All right, day 2, chapter 9, section 3, similar right triangles. Again, we're talking about this diagram situation. This is a very unique case where I am dealing with this right triangle, this major right triangle, as shown by this 90-degree angle up here in the corner. And then what's going to happen in these diagrams in this section is it's going to be split with what we call an altitude, going from that 90-degree corner down to its hypotenuse, and simply splitting up this triangle into two smaller triangles. And the unique scenario that happens as a result of this situation is that I end up with 3 triangles. That's not unique in itself because, again, I have a large triangle, and then when I split any triangle, whether or not it's an altitude, but when I split any triangle, I have 2 smaller ones on the inside. But because of how this is split, I get this unique situation where each of the 3 triangles that is created is going to be similar to the other. Now, what does that mean? Again, that's a chapter 8 reference referring to the fact that each of these 3 triangles is a scale model of the other. Okay, for instance, the largest of the 3 scale models here will be the whole triangle. The smallest of the 3 is going to be this smallest triangle created. And then the middlest of the 3, I guess you could say, would be this other guy right here. They are each scale models of the other, whether or not they're magnifications or reductions, depending on which direction you go. And the useful bit of information there is that if I have this scenario, I can use the fact that they are similar to each other to solve for missing segment lengths. For whatever reason, whatever practical purposes, whether it's an algebra problem like we see in this section, or a real life example where I have the situation and I want to find some specific distance in this diagram, in any of the cases, because of the similarity, I am able to set myself up with an equation to solve for those missing pieces. Okay, so again, in yesterday's example is simply an intro to this about how given a diagram, just mostly getting us used to the fact of this density that we're going to see of information here, how I can create ratios to set myself up with an equation that compares 2 fractions, do cross multiplication to solve for missing pieces. Okay, we're going to continue on today with the same sort of thing, but we're going to talk about a couple of very specific scenarios within this family. So same diagrams, just different information given. And right now, let me skip down to the actual 2 theorems themselves, and then I'll come back up here and I'll talk about the meaning of this junk up here. But let's first talk about these situations. So let me point out a couple of things that you're seeing on your screen right now. Okay, this is known as the geometric mean theorem in regards to these right triangles. And the first thing I want to point out is that each of these situations is the exact scenario that we've been talking about throughout this section so far. Okay, I have a large right triangle that is given this altitude that splits it up into 2 smaller ones. And in each of these cases, I still end up with 3 triangles, all of which are similar to one another. And as such, I can follow the same strategies as we did yesterday, where I find corresponding pieces and I create ratios to solve for missing pieces. Okay, all of that stuff still applies. But what these 2 theorems refer to, and by 2 theorems, I'm talking about the geometric mean theorem has 2 different applications, either for solving an altitude, okay, if I know the length of this piece, or if this is the piece I'm trying to solve the length of, for whatever reason, there's a shortcut way to solve for that bit. Or if I'm being asked to solve for either of the legs of the major triangle. The legs, again, being the 2 sides that create the 90-degree angle, whereas the hypotenuse is the side opposite that right angle. So what 2 situations are we talking about here? I'm either solving for the altitude, in this case, or I'm solving for one of the 2 legs, one of the 2 sides of the major triangle. Okay? And so each of these beneath each of these diagrams represents shortcut ways I can just immediately set myself up with a formula. Okay, and again, I'll refer back to what this is talking about in just a minute. But let's look first at this altitude theorem. So let's say I'm given this diagram and I need to solve for the altitude of this diagram. Well, based on this information, and in the margins over here, I've kind of shown the traditional way of setting up the ratios. It may seem a little busy right now, but I'll come back to that. Immediately, the shortcut thing I can do is I can say, well, whatever this is right here, this altitude, And more often than not in these examples, it's going to be some unknown, some x variable. Whatever that is, this altitude, square it, and it's going to equal the product of these two pieces. What two pieces? This piece here and this piece here. In other words, it's the two pieces that are going to make up the large hypotenuse. Okay, whatever these two pieces are going to be, they'll make the large hypotenuse. I'll multiply those pieces together. They equal the square of the hypotenuse, or sorry, the altitude. Okay, that's what that translates this as. So where did that come from? Again, I've kind of derived it over here. In this case, it takes two of the three triangles that we see, compares them with similarity, and I can set myself up with these ratios. I'll illustrate this in an example, so I'm not going to go super into depth with the origination of that, but you'll see that in the example. And then for solving for either of the legs, maybe my unknown is this short leg here or this longer leg here. In either case, I give you the shortcut way to solve from both here. So AC, the short leg, would be this second formula, where the square of this leg, if this is my unknown, it'd be x squared, is equal to the product of these two pieces. AD being, again, this small piece right here on the same side as that piece that's my unknown. And then the whole hypotenuse, AB. So in the previous one, it was both pieces individually. In this one, it was the piece and then the whole hypotenuse. And then for CB, the other leg, it'd be that unknown squared is equal to the product of this piece, the same piece on the same side as the leg I'm trying to solve for, and then again, the whole hypotenuse, AB. So those are the three shortcut formulas, but again, I'm going to do the two examples today. Will kind of show you the derivation of where I'd set it up traditionally, and then how it would immediately lead to these shortcuts, and how you could almost start with that. But I'll show you that in just a second. But really briefly, let me just talk about what this is meaning right here. What is a geometric mean? The namesake of this theorem we're talking about. A geometric mean says this. Essentially, this right here is the formula for a geometric mean. It's some value squared equaling the product of two different values. Okay, so let me describe that. So for instance, let's say this left side was 16, which I can take the perfect square of. Okay, a geometric mean does not necessarily mean taking the square root of something. Geometric means that I can take the product of two things that also happens to be a perfect square. For instance, 16. Well, 4 times 4, yes, would make 16, but also 8 times 2 would make 16. And so what another way to describe this would be like, what is the geometric mean between 8 and 2? What is the geometric mean between 8 and 2? Well, 8 and 2, I would multiply them together. That'd give me 16. The square root of that 16 would give me 4. So the geometric mean between 2 and 8 is 4. Okay. If I were to pick two random numbers, what's the geometric mean, or the mean, just to kind of remind us, mean means average. What's the geometric mean between 9 and 15? Well, first thing I would do is I would multiply 9 and 15 together, and then I would take the square root of that. So 9 times 15 gives me 135. And whatever the square root of 135 is, that's the geometric mean of 9 and 15. Okay, so that's where that comes from. So how's that applied to these cases? If I were to work backwards from what the geometric mean is, and say make this x times x, and then do the reverse cross multiplication, I get to this piece right here. Okay, where I compare two fractions, two ratios. This is very similar to what we've been doing with since chapter 8, where I compare corresponding pieces to corresponding sides, right? Now, if the piece I'm solving for happens to be an element of both pieces, then I end up with cross multiplication getting right to the geometric mean formula. So that's where that comes from. The only real reason they bring this up is because it's like a unique situation. It's kind of a unique application of this key term. And so it's worth noting, even though it doesn't really give you any further insight into what's happening here. But at least not directly. There are kind of higher level mathematics reasons for why a geometric mean is important, but I'm not going to get into that here. So let's just go into our examples. Okay, I'm going to be doing this mostly on the whiteboard. I'll be referring back to both of these sets of shortcuts, but this is what we're going to be seeing. And what I want you to notice here is that we still have our similar setup for the diagrams. Okay, so how are we going to be applying this in our section assignment? How are we going to see this on a test? You're still going to see your similar kind of diagram setup here. All right, I have a large right triangle split up into two smaller right triangles. All three of the triangles that you're going to see in each of these diagrams are going to be similar to one another, and then you're going to be given information. Now, what I want you to notice about the information given in each of these guys is it is less information than what we did in yesterday's example. So these are going to be ways where I can apply very, very specific pieces of information. So let's jump to the whiteboard and solve both of these examples. All right, part A. Again, we're going to see our familiar diagram. We're going to see a large right triangle as shown with this right angle. Now, another thing that's different with this set of examples is that these are not going to be labeled triangles, and we're not going to see names for the vertices or anything like that. But then what we'll see here again is we're going to see an altitude going from this right angle down to its hypotenuse. Okay, and it's an altitude because it's going to make a right angle with that hypotenuse. So we'll see something like this. There's that familiar diagram that's going to be the namesake for this section. We now have three triangles that are created. Each is a scale model of the other. And then we'll be told some information about some of the side lengths. In this case, we are told that this piece here is 6 units long, and we're told that this smaller piece here is 3 units long. And we're going to be asked to solve for the altitude itself, x. All right, so before I jump to the shortcut, I'll refer back to that in our notes in just a second. I want to show you the traditional way about how we would go about solving for this missing piece. So first off, fundamentally, if I know that I'm dealing with similar triangles or similar figures in any case, I know I can create a comparison of ratios. Some fraction is going to equal some other fraction. And the reason I want to set myself up with this is because I can put my unknown, the piece I'm trying to solve for, in one of these locations and use cross multiplication ultimately to solve for that variable and use traditional algebraic methods at that point. The trick here is that I want corresponding pieces to be over each other in each fraction with same figures being either in the numerator or the denominator. Okay. So in order to set up this ratio, I need corresponding pieces, but I need two of them to compare across this equal sign. So in other words, given the fact that I'm dealing with triangles, I need two sides of one triangle to compare to two sides of another triangle, more specifically, two corresponding sides. Okay, so of the three triangles that are here, I only need to compare two of them, but I do need the two of them to have two corresponding sides. So let's see, of the three triangles here, let's look. First off, let's look at the major triangle, the whole thing. Well, I don't know any information about this side. I don't know any information about this side. So I can't use the major triangle, okay? Because I only have one side to compare, and I need two to compare, right? Now, the two smaller triangles is a different story. I do have enough information between these two guys. So I'm going to be comparing this triangle here to this smaller triangle here. Here's how I know. For this triangle, I have its short leg, x, and I have its longer leg, 6. And in this small triangle, I have its short leg, 3, and its longer leg, x. Now, they happen to share one of those elements, which is why this is going to end up being a geometric mean. But let's apply that. So let's first look at this triangle. Okay, let's look at its long leg. All right, the long leg of this triangle is 6. So that needs to correspond to the long leg in the smaller triangle. The long leg here would be the altitude, which is x. So these are corresponding pieces between the medium triangle, this one right here, and the smallest triangle, this one right here. So now I need to compare them to two other sides between these two triangles. Okay, so I've already dealt with the long leg of this triangle. So now let me deal with the short leg. So the short leg here and the numerator is going to be the x again. So this is where we're going to get our geometric mean. And then I need to compare it to the short leg of my small triangle, which in this case is 3. And there's my ratio. right? Again, comparing corresponding pieces to two other corresponding pieces. Whatever these ratios are, because they're similar, needs to reduce to the same thing. It's at this point that I'm going to use cross multiplication, and now we're going to see the basically the shortcut result that I'll refer back to on our notes. So I would use cross multiplication here. Let's multiply these x's together. That give me x times x, or x squared, equaling these two multiplied by each other, or 6 times 3, which will end up being 18, but let me leave it split up for right now. So based on this diagram, I have the altitude squared equaling the product between the two pieces of the major hypotenuse. Okay, so let me just refer back to the notes to just kind of connect the dots back to what we just did. What we are literally dealing with here is this scenario, okay, where we're being asked to solve for the missing piece being the altitude in our diagram. And so what this says here is that I'm going to take that altitude in this diagram right here, it's CD. So I'm going to take this CD and I'm going to square it. I'm going to set that equal to the product of these two pieces. This piece right here and this piece right here being the two pieces that make up the full hypotenuse. And again, we saw that in our result right here. So based on that theorem, I could actually jump directly here, take the altitude, square it, and set it equal to the product of these two pieces, and I could have just jumped right to here. This is just showing you where it came from. Again, this is the kind of piece, this is what was in the margins of the notes, kind of showing where it came from. Okay, but now I can go through the actual traditional method of algebraically solving for this. At this point, this should be relatively familiar, although we're going to be recalling something from a previous unit right now. So, okay, I have x squared equals 6 times 3. Well, first off, I can do 6 times 3. That is 18. Now, if I want to get x by itself, I need to get rid of the square by taking the square root. That's going to tell me that x is the square root of 18. This technically right here is my exact solution. I have solved for x. X is by itself. It equals the square root of 18. This is what we would call my exact solution. So at this point, just be careful about what they're asking for in the problem. They may ask you to, for instance, round to the nearest 10th or 100th or whatever. And if that's the case, I would actually do this in a calculator. I would take the square root of 18. It would give me 4 point something. Okay. But another thing to be aware of is that this is not a fully simplified version. So this refers back to an older unit, but the next thing I would do, just like if I got a fraction result, I would reduce the fraction. If I get a radical result, I need to reduce the radical. So the first thing to take note of here is that I cannot take a perfect square root of 18. Okay, the square root of 18 is 4 point something, 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 something. Okay, so it's not a perfect square itself. So the next thing I would check for is, does a perfect square divide evenly into this number? So what are my perfect squares? All right, so my smallest one is 4. 4 doesn't go into 18 evenly. My next one is 9. 9 does go into 18, so I could use that. The next highest one is 16, and at that point, now I'm getting into decimals again. So 9 is going to be the one I divide into this guy, so I can actually split this up this way. Okay, for the record, these two are the same exact thing. 9 times 2 is in fact 18. And the reason I'm going to do this is I'm going to apply one of the properties of radicals right now, where I can split this up into two separate radicals. This is equal to the square root of 9 times the square root of 2. Why would I do this? Because this part I can actually take the square root of. That's going to give me 3. This one right here can't be simplified any further. There is no perfect square root of 2. So my final answer, my fully reduced answer, my fully simplified answer is 3 times radical 2. For the record, this is the same exact thing as this. It's just that this is the reduced version of square root of 18. Okay, and we successfully solved for what we needed to. And again, if it asked me to round, I could also go through the process of just doing this in a calculator and getting my decimal result. All right, let's see another one. Again, this one was this illustration was a direct reference to the geometric mean theorem for altitudes, where I'm being asked to solve for a missing piece. And just to show you what, again, from a diagram perspective, what kind of information would I have? It'd be what you see right here. I know some information about the large hypotenuse and being asked to solve for the altitude, okay? Or one of the other pieces. Maybe I know what the altitude is, but one of these two pieces is my unknown. In either case, I can set myself up with that formula. All right, let's do one more and we'll be done with section 3. All right, part B, same diagram, or not same diagram exactly, but a similar diagram. Again, a large right triangle as shown by this little box. And this right triangle, again, will be split with an altitude that goes through that 90-degree angle and connects with its hypotenuse at a right angle. There's our familiar diagram. And again, you'll be given some information. We'll be told that this is the piece I'm going to be solving for here, thus meaning that I'm going to be using the geometric mean theorem for a leg. Okay, that's one of the two legs of the big right triangle. And then I'm told pieces about the hypotenuse. This piece here is 2, this piece here is 5. Okay, at this point, again, I could go directly to the shortcut and just briefly showing you again from the notes which one that would be. In this case, I'm going to be using one of the two leg formulas. It depends on which leg I'm looking at. In this case, in this example, I'm dealing with the short leg here, the shorter of the two legs. So in this case, this one here is this guy. So I'm going to take this unknown value and square it, and it's going to equal the product of these two pieces. AD being this smaller piece, the one on the same side as the piece I'm solving for. So this smaller piece, but then not this piece, but AB being the whole hypotenuse. So I'm going to have to add these elements together. So again, this leg squared is equal to the product of this piece and then the whole hypotenuse. That's ultimately what I'm going to be using as the shortcut here, but I'll show you where it comes from. All right, so again, I need two pieces of two similar triangles, so I can set myself up with a ratio comparing two pieces. This is the traditional way to show it. Corresponding pieces equaling corresponding pieces because I have similarity. So the two triangles I'm actually going to use here are this smaller triangle where I have the short leg and then its hypotenuse. And then I'm actually going to use the large triangle because I have its short leg and then its hypotenuse. I would just have to add these two elements together. So in this case, looking first at the large triangle, I have my short leg here, y, and I'm going to relate that to the short leg in my small triangle right in here, which would be this 2 unit. And then now I'm going to move on to the hypotenuse of my full triangle being 2 plus 5. I know that you would be able to do that in your head. The full hypotenuse here is 7 simply by adding these two elements. But this is just showing you where it comes from. And also maybe it's one of these two pieces you're trying to solve for, in which case your variable will be one of those two pieces. And then that's going to be over the hypotenuse of the small triangle, which in this case is that y value again. All right, so let's just simplify this. 2 plus 5 will end up giving me 7. Right? And so when I do my cross multiplication, here's where we're going to get our basically shortcut version that's in our notes for the geometric mean theorem applied to a leg, where I would have y times y, or that leg squared, equaling the product of 2 and 7 in this case. Now, where did that 2 and 7 come from? Again, according to the geometric leg theorem, geometric mean theorem for a leg, I would take that leg and square it, and then take the same piece on the same side as that leg, this 2, and multiply it by the full hypotenuse by adding those two together. So where did that 7 come from? It came from adding up the full hypotenuse. So this right here would be what you'd be able to jump directly to given the information and given that geometric mean theorem for legs. Okay, well, at this point now, it's just a traditional algebra problem where I'm solving for the variable. So I could actually do 2 times 7. That gives me y squared equals 14. Take the square root of both sides, and I get y is equal to the square root of 14. Again, this representing my exact solution at this point. If it asked me to round to the nearest tenth, hundredth, whatever, I could do square root of 14 in my calculator, and that I'd round it accordingly. If it does not ask for a rounded answer, it wants an exact solution. So the next thing I need to check for is simplifying this radical, just like I would simplify a fraction if I got that as a result. And so the first thing to notice is that I cannot take the perfect square of 14. It comes out as 3 point something. Okay, so then the next thing I need to check for is, does a perfect square divide evenly into this number? Okay, again, going through my perfect squares, 4 is the smallest one. 4 does not go into 14. Next biggest one is 9. 9 doesn't go into 14. And then next after that would be 16. And at that point, I've exceeded this. So what does that mean? That means this is as simplified as it gets. There is no perfect square that goes into square root of 14. There we go. All right, so that leg is the square root of 14. Done. All right, so that is, again, an application of similar right triangles. That will conclude our section 3 notes, and I'll go ahead and end our recording right there.